Boom. Okay. So off we go. So anyway, as I mentioned last time, we had to talk about this lecture. I haven't actually done this lecture in 4 years, so this should be fun. We are going to go through it pretty fast because, again, most of this lecture is for first year chemistry, so that's okay. So acids and bases, new for a lot of you because the Colorado County School District said you don't need to learn this in Chemistry 1, so here we are. So the biggest thing in understanding about acids and bases is the base ion is called hydroxide, and it's OH minus, and the acid ion is called hydronium, and it's H3O plus. And last year, I plunged a light bulb with two big electrodes into a beaker of water, and it didn't turn on. And what did we say about the number of ions that were present? There weren't any. I lied to you. There are some. In fact, in liquid water, there is an equilibrium between two water molecules and H3O plus and OH minus, or you can think of it as an equilibrium between H2O and H plus O minus. Okay? So this equilibrium exists even in the purest, best water, neutralist water there is ions present. So far so good? Okay. Now, there's a couple other things you know. You need to know this is hydroxide, hydroxide. And this is hydronium. Okay? So the H3O plus ion is called hydronium, and the OH minus is called hydroxide. Cool? Now, the H plus by itself, not attached to a water molecule, has a special name because it's named what it is. What is it? What is the H plus ion? It's a proton, exactly. The H plus ion is a proton, and that's all it is. Remember, hydrogen is a single proton surrounded by a single electron. You take away that electron, and you're left with H plus, and it's just a proton. Capiche? All right. How are we doing so far? Hydronium, hydroxide? Now, okay, America.
You switched it earlier. You said the first one was hydroxide.
I was wrong earlier.
Okay.
So yeah, if I did that, I was wrong. H3O is hydronium, this is hydroxide. The base ion is hydroxide, the acid ion is hydronium. Sorry, be patient with me. I know how it is. You know, we have faults. So in neutral water, there is a balance of hydronium and hydroxide. There is specifically, you put little brackets around these guys, there is 10 to the negative 7 molar hydronium and 10 to the negative 7 molar hydroxide. Make sense so far? Okay. The other thing you need to know is P. You gotta know about P. P's kind of fun. P is the same P that you hear about in pH. Whenever I hear pH, you're like, oh, that's acid based. I know pH. pH balanced. My deodorant is pH balanced for a woman, but strong enough for a man. Remember that commercial? Oh, you would have been like 4? I don't know. Anyway. So P is the negative logarithm. So P is the negative logarithm. So when you see P, what you're really seeing is the negative logarithm of a value. Sure. If you took this relationship, I'm going to make it bigger, so yeah, I'm going to start over here and say H2O is in equilibrium with H plus OH minus. So far so good? Now, let's get rid of the equilibrium sign and write an equal sign. And then put brackets around everything. Okay. So remember what an equilibrium expression is? You learned about an equilibrium expression. If you don't remember what an equilibrium expression, it's EQ is given by a big K value, and it's the concentration of the products over the concentration of the reactants. Remember this?
Yes.
Sometimes it's KEQ, sometimes it's KP, sometimes it's KC, K equilibrium concentration, equilibrium pressure, but KEQ, it's the concentration of the products over the concentration of the reactants. Cool? Now understanding this, applying that to the equilibrium that exists between water molecules and hydronium hydroxide, you could write the K, I'm going to call it KW, as the concentration of the product, H plus, the concentration of the reactant, or sorry, other product, hydroxide, over the concentration of water molecules. What's the concentration of a pure substance? Effectually ignored. It's effectually infinite. So we ignore it. We don't write the concentration of anything but aqueous species or gaseous species when we're looking at a gaseous equilibrium. Remember equilibrium rules? Okay. The equilibrium rules tell us that we don't write the concentrations of liquids or solids or gases in aqueous systems, and in gaseous system we only write gases. Okay? So what is H2O here? It's a liquid. So the concentration of a liquid can be ignored. It's basically as high as it wants to be. It's ignored. And there goes our denominator. Just becomes 1. And that's our relationship. Kw equals the concentration of the hydronium multiplied by the concentration of hydroxide. By the way, fun fact, I just learned this summer. The concentration of pure water is actually 56 molar by the definition of concentration.
56 molar what?
Water. So
Wait.
if the concentration of pure water is effectually infinite, but if you look at the mathematical definition of molarity, it's 56 molar. So if you can figure out why that is, figure it out and tell me tomorrow. I know why it is. I'm just curious if you're interested enough in science to figure out why that is. Technically, the concentration of a pure liquid is infinite. It's pure, okay? But mathematically, when you look at the mathematical model we have for molarity, the concentration of pure water is 56 molar. Fun fact. Anyway, okay, so this is the concentration Kw, the equilibrium Kw, multiply the concentration, multiplied by concentration. Now, when you put these values in, values for hydronium, this is 10 to the negative 7. What's the concentration for hydroxide? 10 to the negative 7. Which means the Kw would be what? 10 to the, please don't say 2 times 10 to the, 10 to the negative 14. Yay! Okay. So 10 to the negative 14. Okay. When you multiply numbers with exponents, you add their exponents. So 10 to the minus 7 multiplied by 10 to the negative 7 is 10 to the negative 14. Now, you know why the pH poster stops at 14. pH poster's over here. Starts at 0 and goes to 14. Did you notice that was there?
No.
Yeah, it's there. I had a really big one, but I left it at Spring Valley when I came to Boulder City. Yeah.
Can you remind me what you said about what gets left out of the equilibrium?
Liquids, solids, and gases in aqueous state, in aqueous equilibria, and everything but gases in gaseous equilibria. So when we're doing gaseous equilibria, you only pay attention to gases. When you're looking at aqueous equilibria, you only look at aqueous substances. For now?
Oh, gracious.
No, I mean, just like in this class.
Okay.
As far as like AP chemistry, freshman level chemistry, they just want aqueous equilibria, all aqueous. Gaseous equilibria, all gassy. If you go on to make cosmetics, making $500,000 a year, then the rules change a little bit. But we're learning about all aqueous or all gas. All right, so are we good here? So pure water, glug, 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 10 to the negative 7 molar, 10 to the negative 7 molar, product is 10 to the 14. Cool? Now, when you take the logarithm of a product, what do you do to the things that you took the product of, the logarithm of?
Base.
The product of a logarithm is the right, sum of the logarithm.
Okay.
So the product of the logarithm is the sum of the logarithms. So if I logarithm the whole thing, I'm going to log the whole thing, then the logarithm of 10 to the negative 14 equals the logarithm of 10 to the negative 7 times the logarithm of 10 to the negative 7. If I log the whole thing, then this side becomes what? What is the logarithm of 10 to the negative 14?
Like, are we rewriting it?
Yes. So if you take the logarithm of 10 to the negative 14, it becomes negative 14. The logarithm of 10 to the negative 14 is negative 14. I remember. Okay. Oh yeah, logarithms. Yeah. I remember that. I'm not. Please don't tell Mr. Schultz. Okay. Yeah. So and the logarithm of 10 to the negative 7 is
Negative 7.
negative 7. And then if you take the logarithm of the product, the answer is the sum of the logarithms. So this becomes plus negative 7. Yes?
I told Mr. Schultz about the metric system thing,
Mm-hmm.
and he said he was born in America.
Yeah. Yes, but that doesn't mean we have to stay that way. I was born young and stupid. I didn't stay that way.
Yeah.
As you can see. I had a neck that worked back then. Anyway, I won't get into it. So, does this make sense what we just did? Loggy, loggy, loggy. Now, P is not logarithm, P is the negative logarithm. So, if I negative logarithm this, and negative logarithm this, and negative logarithm this, this becomes not negative 14, but 14. And this becomes not negative 7, but, and this becomes not negative 7, but, did you know 14 equals 7 plus 7?
What? No way.
It's true.
I knew that. I did.
Alex knew. She's like, I got you covered. So, let's look at some really cool relationships that exist because there is a balance of hydronium and hydroxide in water. And here's the relationship. pH, which is the negative logarithm of the hydronium ion concentration, plus pOH, which is the negative logarithm of the hydroxide concentration, equals, anyone know? 14, exactly. pH plus pOH equals 14. And the hydronium ion concentration multiplied by the hydroxide ion concentration is 10 to the negative 14. Those are very, very handy relationships. And there's more.
The H3O.
H3O, yes. H3O plus and OH minus. Okay? You ready for the next one? Here's the next one. I'm going to, in a little bit, show you the equilibrium relationships that exist in weak acids. I'll talk about the difference between weak acids and strong acids. But until then, let me just give you this, because you're probably putting this in a big box with a star around it, and like you're drawing with flowers and things. The pKa plus the pKb equals the pKw. Yeah, you haven't seen these yet. But since you're writing important relationships down, this is a good one to have written down too. Oh, and what is the pKw?
The thing over there. Yep.
What we just
The
did.
opposite log thing.
It's 14.
14.
The pKw is 14. It is the negative logarithm of what we call the water's auto-ionization constant. Okay, so write that down. Auto-ionization. It's nothing sexual. Auto-ionization is what water does as it splits into ions, hydronium and hydroxide. Auto-Ionization.
Like auto, like AUTO or O?
Auto as in like
Okay.
the car. Auto basically means by itself. So an automobile, do you know why why an automobile is called an automobile?
Because you don't have to push it.
Because it doesn't require a horse. It's a vehicle that goes on its own. Automobile. So yeah, basically automobiles are something like your bicycle is not an automobile, but your RC car is.
So if you make automobile that can drive by itself, is that a person that's an automobile?
Yeah, it's an autonomous automobile. Yeah. So yeah, an automobile. The reason automobiles are called automobiles is they don't require horses. They're vehicles that move by themselves. So auto-ionization. Yeah, question.
What do you mean? The definition of if you connect
Auto-ionization. It is what happens when water breaks into its hydronium and hydroxide ions. And the value of auto-ionization is 10 to the negative 14 or 14. That is the auto-ionization constant. PKW or KW. Did I write it? I have to make a great picture of it. Not here yet. So the KW is actually 10 to the negative 14. That's the auto-ionization of water, KW. 10 to the negative 14.
breaks into its ion.
Yes. So water auto-ionizes into hydronium and hydroxide. And everybody's happy. Okay?
But
Right.
isn't hydronium and hydroxide one's the acid, one's the base?
Yep.
So
Well, one is the acid ion, one is the base ion. The hydronium gives acids their acidity, and the hydroxide gives bases their basicity. And I'm sorry, when I say basic, I don't mean Henderson, and I don't mean simple, I mean not acidic. The opposite of acidic. Does that make sense? So like basic high school is like, it's simple high school. No, it means it's not acidic. Acidic high school somewhere else.
So doesn't basic high school like doesn't basic stand for something?
I think it's a road. Yeah.
So on a scale from 0 to 14, is pure water 7 or 14?
7. Okay, so now let's talk about the pH scale. So we have this thing called the pH scale, which starts at 0 and ends at 14. It doesn't really start at 0 and end at 14. But the usual scale starts at 0 and ends at 14. Things that go from 0 to 7, or sorry, 0 before 7, are considered acids, and things that go from more than 7 to 14 are considered bases.
So then what's 7?
7 is neutral. When we have a pH of 7, remember, this relationship. When we have a pH of 7, what's our pOH? If our pH is 7, our pOH is 7, because the two have to equal 14. That means there's exactly the same concentration of hydronium as there is hydroxide. If you have a pH of 6, what is bigger, 10 to the negative 6 or 10 to the negative 8? 10 to the negative 6 is bigger. If you have a pH of 6, that means the concentration is 10 to the negative 6, and pOH is 8, that means the concentration of hydroxide is 10 to the negative 8, and you have an acidic solution. So 0 through below 7 is acidic, and above 7 to 14 is basic. Yes?
So would you want your water more basic?
I want my water to be around 6,
Okay.
ideally. And the reason is, when you have minerals in solution, you make a basic solution, and minerals are tasty, yucky. And when you have an acidic water, it's because you have carbon dioxide dissolved in water. Alex?
Wait, so pOH was 6, then would it be basic?
Yes, exactly. If pOH was 6, that would mean your pH is 8, and you have a basic solution. Right?
So why is the scale pH not pOH? Or
One less letter to write, I think.
is this just basically the inverse, right?
Yeah.
What's the pOH scale?
The pOH scale would be
Would it start at 14?
flip. Yeah, it would start at 14 with battery acid. It would go to 0 with drain cleaner. Lie.
Yeah, it is, but.
Rat poison.
Or drain cleaner.
Or that weird drain cleaner that actually has hydrochloric acid. Go figure. Okay, how are we doing?
Muy bien.
Muy bien? Okay, cool. Let's see, which is the button that goes this way? Hey, look at that.
Mr. Bowers?
Yes.
What else is lye used?
Decomposing bodies. Yeah, so you put lye. Bases are hygroscopic. They like to absorb that water. Lye. Sorry, Brett, go ahead.
Don't you use lye wing soap too?
Yep, you do. That's called saponification. Fun stuff. But we don't talk about that. We don't talk about fighting. Okay, so some properties of acids. Again, this is low-level stuff. This is first-year stuff. No one's going to ask you on the AP test, tell me about acids.
What do
But
they taste like?
yeah, what do they taste like? But just to give you some reference point, acids taste sour. So when you think about acids, think about like orange juice, lemons. Yeah, acids taste sour. Yeah. They react with bases to form salts and water. We're going to talk a lot about neutralization probably tomorrow. They react with metals, dissolving metal atoms into their ions and releasing H2 gas. So sometimes pretty vigorously. We found out yesterday.
Yeah.
It bubbled all over the place. So I'll show you what that reaction looked like.
Blue on blue doesn't look good. Blue on blue.
I know. It says, turn blue litmus paper red. Again, if you were learning this in first year, you'd have a lab where you took litmus paper home and tested things. We might still do it because it's kind of fun. Why not? But this is one of the things you really should know. Acids turn litmus paper to red. Acids turn litmus paper red. And litmus paper is what we call an indicator. And we are going to be playing around with acids a whole bunch.
Yes.
Yeah. Okay, so one of the labs that you guys did, what can I erase? I'm going to erase this whole side. One of the labs that you guys did last year in the gas laws lab, where you made hydrogen gas.
Dissolving zinc in HCl.
Exactly. So remember you dissolved zinc in hydrochloric acid, you collected that H2 gas in the weighted cylinder, then you made it go pop. So what you did is you took zinc metal and you reacted with HCl. HCl was aqueous, zinc was solid, and it made H2 gas, which went blah, 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 blah.